this lecture may be considered as a real basic introduction to vector fields. Okay, we're going to be working with vector fields and forming, I guess we'll be looking at an idea called vector calculus. Very important, very important. Lots of applied concepts associated with vector calculus, like this divergence and curl and a few other things as well. But before we get down to that, we really would like to study a bit about vector fields. Now, it's my understanding that students don't really understand what vector fields are. They can calculate divergence, they can calculate curl, but they don't really understand what a vector field is. So the motivation for this lecture is to give you some understanding of a vector field and get you sketching some of the vectors associated with vector fields. Okay, so what is a vector field? All right, well, a vector field, say in the plane, basically assigns a vector with each point in a given region. So you can see a couple of pictures here in the xy plane. If you're at any point in the xy plane, you can see basically you've got a vector associated with that point. Now you can't draw in all the vectors associated with all the points, okay? You'd have no room to do anything else. So what these pictures are doing are giving you some sort of idea of the structure of each vector field. So over here I've got a basic vector field. So x and y are the independent variables. And you can see here that I input x and y and I output some vector. So let's say I'm at the point 1, 1. So x equals 1, y equals 1. According to this vector field, this vector here would be the vector I plus j, or 1, 1. Okay? Now, let's have a look at this particular vector field. This vector field's defined through this expression. And what we've done is we've drawn in a few of the vectors associated with the field at various points. Now note, of course, that vectors have a direction, they point in a direction, and a magnitude, a length, as long as they're not the zero vector. So you can see in some of these pictures that, well, this vector field certainly has different properties to this vector field. Okay? Over here, we call this particular vector field a so-called radial field. Well, let me draw in a little picture. Okay, if I was drawing a circle with, say, some radius, in this case the radius is going to be something like √2, you'll see that all the vectors on that that circle have the same magnitude. Okay? So they're all pointing away from the origin, right? You can see on that circle, all the vectors have the same magnitude, the same length, and they point sort of away from the origin. Now, in this one, you can hopefully see that there looks like there's some sort of rotation. It appears that way. And no matter where you are, the vectors have the same length. Okay, so actually, if you work out, say, the magnitude of this vector, you actually get 1. So this spin field is a special vector field whereby the direction changes depending on where you're at, but not the magnitude of the vectors involved. Okay, so that's a couple of basic ones. Here's a couple of other ones. So this is basically the same as your radial field, except we've got minus signs. So you would expect the vectors to point in the opposite direction. So instead of pointing away from the origin, they're all pointing toward the origin. Here's another vector field. So here we've got minus yi minus xj. We had something a little bit different over here, and there's the I guess a sketch of some of the vectors associated with that. Okay, so mathematically speaking, a vector field is just a function, a vector valued function, and the components f sub 1 and f sub 2 are functions in say in 2D of two variables. So that's the basic case. Sketching these sort of things in 2D is not too hard. It does require a little bit of thought, but it's certainly more difficult in 3D. So let's have a brief look at 3D. Here you've got functions that depend on position, x, y, z. And of course, you're going to output some three-dimensional vector for each value of x, y, and z. Okay, so here's an example involving the gravitational field. They point towards the center of mass, that are the source of the field. And we've already, in this course, computed vector fields by computing the gradient field of a function. We know that, let's say this is the blue region is some surface, say this. If I compute grad f, then at every point the gradient's a vector, and that vector will be perpendicular or normal to that blue surface. Okay? So, at each point on this surface, you've got a vector field associated with it. Okay? Now, here's a couple of pictures, I guess, involving fluid flow. On the left-hand side, we've got a cross-section of the wing of an aircraft, an airfoil. And you can imagine this in, say, some lab, whereby you put it in a wind tunnel, generate some streamlines by using kerosene smoke. These vectors here are just the velocity vectors. Okay, so a long vector would mean a faster flow, a shorter vector would mean a slower flow. Similarly, on the right-hand side, we've got a contracting channel, and you've got streamlines there. And again, you can think of these vectors as being tangent to, I guess, the path that a particle would take through that channel. Okay, you can see that as the channel gets narrow, the vectors get longer. So that would indicate that the velocity vectors increase. Okay. Okay, well, that's some basic ideas where simple phenomena can be reflected by these vector fields. Now, I think this is a really interesting situation. In this particular diagram, what's happening is we're measuring wind velocity. Okay, so there's a picture of certain winds moving around the Earth, but I'm not sure if you can see it on the picture. All the arrows in that picture are the same length, but however, what they've done is they've used colour to indicate the magnitude of wind speed at certain points. So there's a bit of a scale there. Blue means the magnitude is small, whereas yellow means the magnitude's quite large. Okay, this is quite good if you can do it. It's hard to draw it by hand, of course, but I think that's great. I think that's really, really interesting. All right, so I've given you some idea of how vector fields are useful, but let's just spell it out a bit. The difference between real valued functions and vector valued functions and vector fields, one of the important differences is the following. Well, a scalar valued, a real valued function can change one of two ways. It can increase or it can decrease. Right? Or I guess it could stay the same. Right? But on the other hand, vector valued functions are a lot more flexible. Okay, so what do I mean when I say that? Well, a vector valued function can change not just in magnitude, but also in direction. And depending on what we want to measure, a vector valued, say a vector field, can, the rate of change, loosely speaking, can be interpreted as a number or a vector. So this is a lovely illustration of the importance of the topics we're going to study in this section. Okay, the flexibility, accuracy, and modelling, really important, really important. All right. Now, like I said before, my experience is that students don't really understand vector fields. They can do calculations with them, but they don't really understand their structure very well. And one of the reasons is that there's not much time to talk about vector fields and sketching vector fields. For example, at school, you spend a lot of time on curve sketching techniques, right? Sketch, you know, x squared plus 2x in the xy plane. You know, sketch this function, sketch that function. Unfortunately, we don't have very much time to sketch vector fields. Okay, so I just wanted to spend a few more minutes sketching a couple of the basic vector fields that we might see along the way. Okay, so we would never ask you to sketch really complicated vector fields because it's just too much work. But simple ones are not too bad. So let's have a look at the following one. So if I wanted to write this out in IJK notation, it'd be something like this. Okay. So let's try to sketch some of the vectors in the plane, in the xy plane, associated with this vector field. Now for me, a good place to start is on the axes. Okay, so that's a good place to start. Now let's also look at the structure of our vector field. There's no, like the j component, or I guess the j component is 0 here. So can anyone say anything about what we would how we would expect our vectors to point? Yeah, they'd be horizontal, exactly. Okay, there's no j component, so we would expect all the vectors associated with this vector field to be horizontal, or parallel to the x-axis. Okay, well, let's start, say, on the y-axis when x equals 0. Well, when x equals 0, what am I going to get here? I'm going to get the 0 vector. Okay, so these are the points on the where x equals 0. We'll just get, well, we won't get anything there. We'll just get nothing. What happens, say, if x equals 1? Well, if x equals 1, I'll get the vector 2i. So if I draw in the line x equals 1, I'll have vectors two I vectors all along it. So say that the line x equals 1's there. Okay. Now, what happens if I put in the substituting the x equals -1? Well, that's just down this line, but I'll get minus 2i here. So they'd be the same length as these guys, but pointing the opposite way. Okay? So the length, the direction's still the same as these guys, but the length's increased, the magnitude's increased. Okay, and similarly on the other side, the magnitude will increase and keep the same direction as the vectors that are already on that side. Okay? So that's a basic sketch of that vector field. You can see it's trying to, I guess, diverge from the line x equals 0. Let's look at another one. Let's, I don't have this slide here, but let me write it down anyway. Say, minus xj. So this one's a little trickier. It's got a 0 function associated with the I vector, but what we would expect our vectors to point vertically, right? Because there's only a j component there. Okay, so now when I say vertically, I'm being a little bit imprecise, because in this case some of them will point up and some of them will point down. Okay, so when x equals 0, what am I going to get? Well, I'm just going to get 0. So along that axis, I don't have anything. Let's look at along the x-axis. What's going to happen? Well, if I move this way, this is going to become, so for x positive, this is going to be something like, minus j, minus 4j, minus 5j, minus 6j, etc. Okay? So the vectors on this side will point down. Now if I move this way where x is negative, I'll get a positive value here. So these vectors will point up. An increasing magnitude as you move away from the origin. Okay? Now, of course, along this line, the magnitude of the vectors and the direction will stay the same. So you can sort of, draw those in, draw these in, and form your vector field like that, okay? Now if you wanted to be a little bit particular about it, you could draw a line here and match the tails up with the heads on that line. But I'll leave you to draw a few more vectors in and see if you can get a feel for it. Questions? Oh, they might, depends which ones you draw in. I've drawn them in not to overlap, okay? That's a very good question. The question was, what about when, if you draw vectors in that overlap? Well, I wouldn't do that because it sort of defeats, it can defeat the purpose of what you're trying to explain, right? So, I wouldn't draw vectors that overlap. Choose them so they don't overlap.